How long did it take for the human eye to evolve? How many iterations were there before we arrived at two round eyes able to distinguish light and dark, pick up different wavelengths that convert to colors, and focus on objects near and far? What the human eye is capable of today took millennia upon millennia to develop. In the past few centuries, we have also evolved our own technological response to capturing, recording, and interpreting light. This evolution has been fast. Let's take a look. This is ASU. The first part of a camera, which interacts with photons of light from the environment, is the optics of the camera. Of course, the first camera had no optics or lenses, just a singular hole called a pinhole, which blocked out rays of light except for a single ray passing through the center of the hole. This would form an inverted image on the opposite side and gave rise to the word camera obscura, or dark chamber in Latin, which is also the name for cameras. Pinhole cameras were used extensively throughout the Renaissance period. However, pinhole cameras had a severe problem. They lost too much light due to their small pinhole, making it difficult to use them in dark environments or when an object is moving in the scene. A lens is the update of a pinhole, allowing the focusing of light rays rather than blocking them out to create a focused image. But this came at a cost. You couldn't keep the whole scene in focus, as the bending of light is governed by the lens design and curvature. But the lens is the workhorse of the modern camera. Its size and shape govern the optical properties of the system. Computational cameras go beyond traditional optics of a lens system to recover more information from the visual environment. Changing the optics of the camera can include introducing new optical layers which mix rays of light in special patterns that can be decoded later. Light scatters, bends, reflects, refracts at these optical interfaces, and this physical knowledge can be used to infer information about the light paths traveled in the scene to the camera. For instance, lensless cameras utilize diffractive optical masks or coated apertures above the camera, allowing the computer to refocus a blurry image after capture and enabling applications such as 3D photography. These cameras can be made ultra-thin and are useful for space-constrained applications, where a lens would be too bulky to deploy on the camera system. Another example is using natural phenomena such as water droplets on a pane of glass. Researchers from the University of Bonn were able to reconstruct 4D information of light from how light bends through water droplets, allowing them to recreate new views of the scenes from different angles. Computation is the new lens, and we can utilize more unusual lenses and optical layers in our cameras while extracting pretty pictures, and even more useful information from the resulting captures. The human eye developed after a long process of evolution, and the camera has developed to its current place through many iterations. Cameras we routinely use nowadays have phenomenal power to capture and process light information. We see and record and interpret so much more. Computational cameras will help us see the future of photography. This was ASU. Thanks for watching.